Good morning, this is Professor Will, CBMD PhD. It's Tuesday, November 10th, 2020. It is 6:09 and 8 seconds a.m. Eastern Standard Time, and this is my research on astronomy. So let's get started here. First brown dwarf discovered by radio observations confirmed. Date November 9th, 2020. Source Association of Universities for Research in Astronomy, AURA. Summary. New research has led to the first direct discovery of a cold brown dwarf from its radio wavelength emission, along with paving the way for future brown dwarf discoveries. This result is an important step toward applying radio astronomy to the exciting field of exoplanets. For the first time, astronomers have used observations from the LOFAR radio telescope, the NASA IRTF operated by the University of Hawaii, and the International Gemini Observatory, a program of NSF, NOIR Lab, to discover and characterize a cold brown dwarf. The object designated BDR J1750 plus 3809 is the first substellar object to be discovered through radio observations. Until now, brown dwarfs have been uncovered in large infrared and optical surveys. Directly discovering these objects with sensitive radio telescopes such as LOFAR is a significant breakthrough because it demonstrates that astronomers can detect objects that are too cold and faint to be found in existing infrared surveys, maybe even large free-floating exoplanets. In this discovery, Gemini was particularly important because it identified the object as a brown dwarf, and also gave us an indication of the temperature of the object. The Gemini observations told us that the object was cold enough for methane to form in its atmosphere, showing us that the object is a close cousin of solar system planets like Jupiter. Brown dwarfs are substellar objects straddling the boundary between the largest planets and the smallest stars. Occasionally dubbed pale stars, brown dwarfs lack the mass to trigger hydrogen fusion in their cores, instead glowing at infrared wavelengths with leftover heat from their formation. While they lack the fusion reactions that keep our sun shining, brown dwarfs can emit light at radio wavelengths. The underlying process powering this radio emission is familiar, as it occurs in the largest planet in the solar system. Jupiter's powerful magnetic field accelerates charged particles such as electrons, which in turn produces radiation, in this case radio waves, to an aurora. The fact that brown dwarfs are radio emitters allowed the international collaboration of astronomers behind this result to develop a novel observing strategy. Radio emissions have previously been detected from only a handful of cold dwarfs, and they have been known and catalogued by infrared surveys before being observed with radio telescopes. The team decided to flip this strategy using a sensitive radio telescope to discover cold faint sources and then perform follow-up infrared observations with a large telescope like an 8-meter Gemini North telescope to categorize them. Researchers asked themselves, why point our radio telescope at categorized brown dwarfs? Let's just make a large image of the sky and discover these objects directly in the radio. Having found a variety of telltale radio signatures in their observations, the team had distinguished potentially interesting sources from background galaxies. To do so, they searched for a special form of light that was circularly polarized, a feature of light from stars, planets, and brown dwarfs, but not from background galaxies. Having found a circularly polarized radio source, the team then turned to telescopes including Gemini North and the NASA IRTF to provide the measurements required to identify their discovery. Gemini North is equipped with a variety of infrared instruments, one of which is usually kept ready to observe when an interesting astronomical opportunity arises. In the case of BDR J1750-3809, Gemini's mainstay infrared imager, the near-infrared imager and spectrograph NIRI, was not available, so Gemini's astronomers took the unusual step of using the acquisition camera for the Gemini near-infrared spectrograph GNIRS instead. Thanks to the careful work and foresight of Gemini's staff, this camera provided deep, sharp, and accurate imaging at several infrared wavelengths. These observations really highlight the versatility of Gemini, and in particular the little-used keyhole imaging capability of Gemini GNIRS spectrograph. This observation showcases both the flexibility and the power of Gemini observatories. This was an opportunity where Gemini design and operations enabled an innovative idea to develop into a significant discovery. As well as being an exciting result in its own right, the discovery BDR J1750-3809 can provide a tantalizing glimpse into the future when astronomers can measure the properties of exoplanets' magnetic fields. Cold brown dwarfs are the closest things to exoplanets that astronomers can currently detect with radio telescopes, and this discovery could be used to test theories predicting the magnetic field strength of exoplanets. Magnetic fields are an important factor in determining atmospheric properties and long-term evolution of exoplanets. The researchers' ultimate goal is to understand magnetism in exoplanets and how it impacts their ability to host life. Because magnetic phenomena of cold brown dwarfs are so similar to what is seen in solar system planets, we expect our work to provide vital data to test theoretical models that predict the magnetic fields of exoplanets. The first unambiguous observation of a brown dwarf did not occur until 1995 after more than 30 years of theoretical predictions. The radiation emitted by the acceleration of charged particles in the magnetic field is referred to as cyclotron radiation. The name comes from a cyclotron, an early type of particle accelerator. Circulatory polarized light is also used to create 3D movies. Good day, this is Professor Will, CBMD PhD on astronomy, computer science, and space and time. Well, hope you enjoyed listening. Until next time, have a great day.